All right, so I want to talk today about maps, specifically vector maps. So you probably all know these already from Google Maps or something like that. And yeah, I want to focus specifically on the portability of maps because that's where it gets really interesting with Rust. So imagine being able to fly from outer space to any place on Earth. This idea was really groundbreaking about 30 years ago. And I also had this kind of breathtaking moment when I first used something like Google Earth. Did anyone also have this experience of using Google Earth, Google Street View, and crazy thing, yeah? The first usage or the first real project for map visualization was TerraVision. And it was developed in the 90s, so it's really old. It actually predates Google Maps or Google Earth, and there were actually legal battles. So Google was not, like Google copied them, basically, but yeah, I don't know, there's a Netflix series about that if you're interested. And yeah, it was the real first usage of maps, and you had satellite images, you could fly through the world. It was already networked, and yeah, I think this is very cool. Quick thing about myself, so I am not really a geoinformatics expert, or I'm not really that knowledgeable in graphics programming. I'm actually right now a security engineer, but before that I had a lot of free time, so that's when I started doing the side project and started looking into map rendering. I currently work at Trail of Bits, which is a security company, so we audit software, so we audited OpenVPN, curl, Linux, and a lot of other software. We also have a lot of Rust tooling available. So one is called dialint, which is basically Clippy, but you can load lints from shared libraries. There's Nesicist, which tests your tests. So it's basically mutation testing, but about your tests. And there's testfuzz, which is similar to cargofuzz, if you know that, but testfuzz works with AFL++ instead. And yeah, apart from that, we're also doing a lot of stuff in the open source world. For example, Sigstore in Python is one of our projects. But enough from that. So I think it's very nice that I'm here. So they sent me, even though this is like totally unrelated. So I want to talk about map visualization and also then about portability of maps. And the great technologies which are closely related to Rust, which make this available. So there's WebGPU, WebAssembly. I want to talk a little bit about threading in WebAssembly. I want to talk a little bit about Rust and about some upcoming features in this renderer and draw some conclusions from that. So the world is really huge, as you all know, and in order to visually represent so much data, you have to split it up. So the most common approach to this is to use tiles. So basically, you just split your world into several smaller data sets. And you arrange these tiles on a 2D plane. And you also want to zoom in and zoom out, so you want to have different detail levels. And as you zoom in, the tiles grow exponentially. So there are like actually billions of tiles if you zoom in to zoom level 20, for example. Yeah, and in order to first get to this 2D plane, you need to have some projection. So this is a very simple or very simple representation of this, but you essentially use some projection to go from a 3D representation of the Earth to 2D plane. There's no solution to this, actually, so you need to have some compromise, and the most well-known compromise is called WebMercator. There are also two kinds of tiles, which you probably also are familiar with, so there are raster tiles and vector tiles. You mostly use raster tiles for satellite images, but you can also use them for different map styles. And there are vector tiles. So vector tiles are essentially SVGs, so you just have a vector representation of your data. And this is actually very cool because then you can change the style on the fly. So for example, you can change the color of water, you can change the color of trees, and that is not possible with raster tiles. On the other hand, rendering vector tiles is more complex, more involved, because rendering a PNG is rather simple. So a vector tile is basically just a set of geometries. For example, you have a polygon here with a hole. You can also have lines and points. So essentially, it's just an SVG. And when you have such a geometry, a complex geometry, in order to render it on your GPU, on your laptop, you first have to tessellate it. So, and tessellate means you take your geometry and turn it into triangles. And this step is specifically computationally intensive, so it's not very easy to create this mesh out of triangles. So that's what I will also talk later a little bit about when we come to WebAssembly and why it's so great. Yeah, now let's take a look at portability. Portability, I think we also mentioned it now a few times during this conference, for example, with regards to packaging, is really a mess, and it's usually very annoying to port your application from one platform to the other. And if you break it down, you have basically a lot of dimensions to it. So you have CPU architecture, you have different CPUs, you have Intel, you have Apple CPUs. On top of that, you have different operating systems, which you then can combine with several architectures. And if you make something which should render an image, you also suddenly have the dimension of graphics APIs. So your GPU only supports a limited set of interfaces, you could say. So that's also something you have to care about. And if you also want to target the browsers, then of course you kind of have the three major browser implementations. As part of this side project, we did some analysis, and we kind of concluded that there currently is no such thing as a portable map renderer. There's Bevy, which you all know and love. That is kind of portable, and it's closely related to the technology stack I'm using here. But I think especially for map visualization, it's kind of interesting. Yeah, there is no portable renderer as of now, so far. And the reason for that is that if you combine several platforms, you just get less and less renderers which support the set. So there are quite a lot of map renderers which work in the browser, but then they most likely only work in the browser. So if you want to have a renderer which works on your phone and in a browser, you suddenly don't have any. And this brings me to the side project that I started. So there's this MapLibre organization, and I'm basically working, you could say, in the research and development part of that, and trying to push like Rust into this direction of making it really a usable implementation for map rendering. So there's currently a C++ implementation and a TypeScript implementation, but yeah, those are not really cross-platform. And yeah, like the name reminds you maybe of some other well-known map renderer, which name I don't want to say really, but it's called Mapbox. And yeah, this basically is the open source fork of it. And yeah, if you pay for your maps, you maybe want to check out this. So let's recap. Like the problem is you have multiple code bases, you maybe have high maintenance cost, and implementing features is just very tedious. Especially like in an open source project like MapLibre, implementing a new feature for a TypeScript code base and a C++ code base is like almost close to impossible in my opinion, because like, yeah, it's so expensive and you have different people, and usually TypeScript programmers are maybe not that fluent in C++ or the other way around. Yeah, so the solution is a single route code base for browsers, mobile and desktop. And yeah, we have to tick all of these boxes, like support different CPUs, GPUs, different operating systems, and all the browsers. So there is this new fancy and very cool technology that is called WebGPU. Has anyone heard about that? Okay, everybody, basically, nice. Okay, so I don't have to talk much about it. Maybe a cool fact is that it's kind of stable in Chrome since a few months. So you can use it. It's still a draft from a spec perspective, so you have to expect it to change. But you can already use it like in the latest Chrome version on some operating systems. And yeah, I just expect it to be stabilized maybe next year, maybe in 2 years, hopefully sooner. And one promise that it actually didn't hold so far is that you have multi-threaded rendering, so you can upload data from several threads. But this is unfortunately something that is not in the first version of WebGPU, so eventually, like WebGPU 2 will allow that. So there have been quite a few graphics APIs over the years. About 20 years ago, there was OpenGL 2. And then it took quite a lot of years until WebGL came into existence. And this is basically more or less the same story with WebGPU. So the style of graphics APIs was really founded by Apple, I would say. So Apple started designing a new API for talking to their GPUs. And this influenced just a whole bunch of these APIs that you know today, for example, DirectX or the more open Vulkan. That is all in the same style, and you can call them low overhead graphics APIs. And that is because you need basically less communication between your CPU and your GPU with these low overhead graphics APIs. And that is basically the reason why WebGPU is here now. We want to have the same benefits of these low overhead graphics APIs also in the web browser. And in my opinion, specifically for map renderers, it is really a game changer because you want to fulfill this goal of reaching any device or any platform, and your device maybe only supports one graphics API. And in my opinion, the real fundamental thing about WebGPU is that it is designed from the ground up to fulfill this goal, to run on any device. And yeah, you could actually say like it's the people who made the spec wanted to find the smallest common denominator between all GPUs. And in my opinion, they made a pretty good job in doing that. There are a few other cool highlights about WebGPU, which is you can have compute shaders for complex simulations on your GPU and use that directly in rendering. So if you talk about maps, that's maybe very interesting if you maybe have some traffic simulations which are heavy to compute. And then you can use that output directly to present it on your screen. There's also better API in WebGPU. There's finally no more global state, which is very nice. There are also better error messages. So it almost sounds a little bit like they borrowed some ideas from Rust. And yeah, it's now this low overhead graphics API compared to WebGL. So you basically have to do fewer calls between your JavaScript or your Rust and your browser, for example. And there's way less boilerplate compared to Vulkan. So if you know Vulkan programming, then you maybe get scared by Hello World being a few hundred lines. So that is really not the case here. There's a really cool implementation written in Rust, which is called WGPU, and it supports older platforms. It also powers Bevy, for example. And the cool thing is that you can use it in the browser. So there's this figure which shows like you have your application that speaks to WebGPU, and through that you reach all the lower level graphics APIs. But you can also reach WebGPU through WebGPU, and that means then you're talking to your browser, and the browser will then talk at some point to your graphics API of choice. Yeah, WebAssembly is the other very important thing in this equation. So WebAssembly, that's the binary format. You can compile from Rust to WebAssembly or choose your language of choice, basically, and you can run it basically anywhere. And there's a really cool working group in Rust, which makes working with WebAssembly really a breeze. Specifically here, I want to talk about multi-threading in browsers because it's actually possible, maybe not that known, and that's also for a reason, maybe. So for renderers, you often want to offload heavy tasks into a different web worker. And you can do that very, very well with multi-threading and WebAssembly. So basically, you can create shared memory in a browser and then run your same Rust code on the same shared memory, and then you can actually use all the nice things from Rust, like atomics. You can use mutexes, you can use channels, The only thing that's really not available is standard thread, and that's for reasons which are that the API in the browser works just fundamentally different than on some Unix system like POSIX threads. You cannot have those lightweight threads. You have web workers, but that doesn't really limit you from having multi-threading. And with multi-threading, I really mean working on some single shared memory from different threads. In order to use it in your project, it's actually quite straightforward. You just have to know all the Rust flags, which are a little bit loosely documented, in my opinion. So you need to enable shared memory. Of course, you also need to be on the WASM target. And yeah, then you want to enable import memory in Rust, which essentially allows you to have one shared memory and then import it into multiple WebAssembly modules. And that is how you reach basically the multi-threading. You unfortunately also have to set the maximum amount of expected memory when you use shared memory with WebAssembly. And you have to enable a few WebAssembly features, like you have to enable atomics and some other more advanced WebAssembly features. Those are all supported basically in every browser nowadays. So if you're just targeting browsers of the past 2 years, you should not have any problems. Some pitfalls. So shared memory is restricted. So there were the Spectre disclosures a few years ago, so these child channel attacks on CPUs. And because of that, you have to jump through a few hoops, basically, to being able to use this. So essentially, you have to make sure that all your resources on your web page come from a single origin. So this means all of your images have to come from a single origin, all of your JavaScript. So this is a little bit annoying, and that's why you need to have some fallback in place, unfortunately. Compatibility with WebAssembly VMs, yeah, you need to make sure that these advanced threading features are available, but they most likely are, actually. And yeah, this memory size problem is a little bit annoying because you have to estimate how much memory will you use. If you just say, yeah, I will be using like 10 gigabytes, then your phone will probably say no. So yeah, you have to find a good size and test it on several devices to be sure. One interesting limitation is that futures returned from web APIs are not sent. So if you, for example, call fetch and you get a future back and wrap that into some Rust future, then that is not sent. All futures from Tokyo, for example, they are sent, so you can share them between several threads. And yeah, this is due to limitations, just how browsers work. So you have to work around that. So quick recap. So with Rust and WebAssembly and WebGPU, you reach the portability in terms of GPU, but also in CPU. So those technologies really fit nicely to reach portability. And with that, we can check all the boxes, and we kind of have renderers which work on any operating system. So yeah, and so in total, you could really say WebGPU, WebAssembly, and Rust, that's the ideal match. And you reach all the platforms, like I said, you reach macOS, Android, iOS, Linux, and so on. And yeah, you can even, with all of this technology stack, you can even render New Zealand. So why oxidize map renderers? It's just want to repeat this again, basically. So why choose Rust? So Rust is a systems programming language. It's memory safe. That's the ideal fit for basically any renderer. So good choice, Bevy. You can have multi-threading with WebAssembly. That's also very nice. But maybe the most important thing is really community. So the WebAssembly community in Rust is awesome. So we already talked today about WASM pack, for example. That's a really great resource. And yeah, something like this doesn't really exist in any other language. Like you could, of course, do all of this more or less in C, C++, but you would miss out on a lot of tooling, and that is what really makes this a breeze. So the projected benefits of using this tech stack is actually increased performance. So especially for this tessellation step, which is very computationally intensive, you can run all of that in WebAssembly, so it will definitely be faster compared to running the same thing in TypeScript. You also reach pixel-perfect equality between several platforms. I would guess, for example, that's not very important for games, but if you're rendering maps and you want to use them for specific use cases, you're actually aiming for pixel-perfect equality between the platforms. And if for any reason it is not equal between the platforms, then it's probably because of some bug in WGPU, so you can basically open just an issue there. In my opinion, this whole tech stack is also really built to last. So WebGPU will define the whole graphics API space for the next 20 years at least, I would say. But it is really built on mature foundations. I already mentioned that you save a lot of time through that. You save a lot of cost, so you don't need to write the same features twice. If you have only a single code base, that's not only nice for developers, but also nice for users, because so if you make your renderer pluggable, plugins for that will run on any platform. So right now, the geo space, in my opinion, is a little bit fragmented. So you have a lot of renderers, for example, for the web, for native, but it's really hard to find something where you can use the same plugins, for example, for all of the devices. Yeah, some upcoming things which are very nice and fun to work on is I really want to get into data visualization. So I want to really visualize maybe also live data. Text rendering is actually a very interesting and cool problem. Unfortunately, it's very hard. Yeah, there also at some point need to be some SDKs which fit the MapLibre ecosystem. So there should be SDKs for TypeScript, Android and iOS, and Linux and Windows as well. And yeah, 3D features is always nice. It's nice eye candy. Maybe sometimes it doesn't really have that much value in itself, but it's something which is fun working on. For example, rendering like 3D mountain ranges or just buildings, and maybe fancy little roof shapes. Yeah, this brings me close to the end. So problem solved, in my opinion, yes. So this technology stack is really awesome for solving this problem. So all of these technologies come together to solve the problem. It is very fast in that sense. So WebGPU brings performance improvements, but also WebAssembly. And yeah. So that's it. So if you also love map rendering, feel free to check it out. You can also try the demonstration if you want. Please don't break it or open an issue if you break it. And yeah, I'm available on Matrix, and there's also the GitHub link. So thank you.